everyone. Hi, Kirill and Vladimir, for joining. Thank you for joining today, and for everyone else that might see this recording later on. I hope you're gonna enjoy it. Today we're gonna talk about open source LLMs. How do you train them, fine tune them, and everything in between. And then the idea would be to go through this process by showing a real world example that we worked on developing MK LM7B, which is one of the I don't know if it's exactly the first, but I think one of the first Macedonian large language models for the Macedonian language. So we're gonna go through the theory, and then we're gonna show in practice how we actually did it, everything that is necessary, and etc. All right, let me just see if I'm right. Yeah, there we go. Shortly about me, my name is Nikola Trajkov. I work as a machine learning engineer. So I primarily work in Python, Spark for big data, and then AWS as my cloud provider of choice. I primarily work as a machine learning engineer, although I've been doubling quite a bit of the whole data field. So data. I've done quite a bit of data engineering as well. And yeah, lately, as probably most people in the field, I've been primarily working with large language models for the last 2-3 years, and that's actually our topic for today. All right, so today we're gonna, as I said, we're gonna go through the example of MK-LLM7B, but we're gonna talk about everything that we're gonna show here today is pretty much the same for any other topic you might have regarding training and fine-tuning LLM. So we're gonna show how we teach a large language model a new language, but it's gonna be almost identical for any other task. If you have a different task that you would like to fine-tune a model for, it's gonna be pretty much the same process, except that for maybe the first part, which I'm gonna note when we get there, for the continued pre-training that might not be necessary if you're not trying to put new knowledge in the model. So first of all, why did we make MKLLM7B? And this is kind of why you might want to fine-tune or train your own model. First of all, we were kind of inspired by some other people that did something similar for their languages in the region. At the time when we started doing this, this was almost a year and a half ago. We did not actually have that many good large language models for the Macedonian language. I think that at that point it was either 3.5 from OpenAI or the Plane 4 that was like the flagship for OpenAI at that moment, and it was the best model for Macedonian at that time. And even that model was not performing as well. It was quite often it was confusing Macedonian with the other local languages like Bulgarian, Serbian, etc. So it was not the best performance. So the idea was to kind of try whether we can do something that is specialized for the Macedonian language. We were not trying to make a competitor of OpenAI. That's impossible. You just need way too many resources and money and everything. So the idea was to make a small model that is a lot smaller, like 20, 30, 50 times smaller than the OpenAI models, and see whether we can specialize it enough so it's it's usable and it works well for Macedonian. Through this, we hope that we're gonna stimulate the local research community and hopefully encourage other similar projects in the community here. And primarily, we also wanted to create desperately needed resources for the Macedonian language. At the time when we were starting this, there weren't at all any. I mean, there were some Macedonian resources as part of bigger data sets out there, like the Common Crawl project, where who basically crawls the whole internet, and they did have some Macedonian data there, but a specialized data that is needed for training and instruction tuning was basically non-existent. Because we're going to see later, in order to fine-tune the model to be able to follow instructions and use its knowledge, you need specialized data sets, which were non-existent at that point. Now, the idea of why you would actually maybe want to have a local model or an open source model and then deploy it yourself or use it in a different capacity. First of all, you're going to get full control over the data, and you can have full privacy. Basically, you can decide where and how you use the model, as opposed to when you're using a third-party API, you have to send the data over the internet, and it's going to be processed somewhere in some data center. So depending, this could be interesting even for specific industries. where regulation says that you got to be sure where the data is treated and processed, and how the models are used. So basically, with local models, if you have enough resources, you could run them either on premise for smaller models, as we're gonna see later, on consumer grade laptops even, and as long as you have the resources to buy primarily the GPU cards, you can run them wherever you want to. Secondly, they could potentially prove that they could be more cost efficient. Now, this is an important note to mention here, is that when you're starting out, and then when you have a lower number of requests, I mean, at the beginning, or even if your requests generally are not that many, then there's no chance that you're going to get better economics by developing or deploying your own model versus using an API. Because for the API, you're basically paying per request, per token per request. And then for open source models, I mean, for local models, you're going to have them deployed all the time. So basically, there's a point in time where it kind of makes sense to switch over. If you're using that many, if you have that many API requests, you're using as many tokens, then at some point you might be in a position where open source or a local deployment might be more cost effective for you. Now, I think that the best case for open source and local models is that they can be adjusted and adapted to your specific needs, and you can do this in any shape or form that you might want to, as long as you have the data necessary to do that. And this allows for organizations to really create competitive advantages that are not available through other means. So I think that one of the biggest selling points is exactly this. Okay, now before we move on, just a very short overview of some theory of how these models actually work like. The idea is that there are many concepts that make large language models able to understand us and be so good. But if we need to kind of separate two that are very important according to me, and that can actually really allow even people who are not in this field to kind of understand and grasp how these models are doing what they're doing, is the concepts of embedding and attention. Embedding is the concept of how do computers actually understand the meaning behind words, because computers are not able to read text. They understand numbers. So the idea between embedding is creating vectors for words, and those vectors have some sort of meaning in them. So it's not just random numbers, but they do have some meaning in those numbers. And this happens while the model is training. It's learning these representations and how they should look like. An example here is, for example, imagine that we have a three-dimensional space, and we have these four words here, and each word represents one vector. So for example, the vector of king is going to be somewhere here, which could be something like 0, 0, 0, 0. And then for man, it could be 0, 0, 0, 0, 1. And then the same thing for queen and woman. Basically, the idea, we can see that king and man are kind of on the same dimension here, which could mean that dimension represents sex. The same with queen and woman, while king and queen are on the other dimension, and that dimension could represent royalty, for example. So the idea is that these vectors are designed in such a way that, for example, when we subtract the vector for the word man out of king, what we're left is, it's the concept of royalty. So the difference is the concept of royalty. If we take that difference and we add it to woman, we're going to get a vector that is very close to queen. So it's not going to be the exact same vector, but it's going to be very close to the vector for the word queen. Basically, essentially saying that in that difference of numbers, the model has the concept of royalty kind of learned, and it knows how to apply it. The same thing with the second example. For example, if we take the vector for the word Paris, we subtract France from it. What's going to be left there is going to be the concept of capital city. If we take that difference and we apply it on the vector of Poland, we're going to get the vector actually a vector that is very close to Warsaw. So that's the first concept that I think is very important in order to understand how these models work. And the second one is attention. Now, when we say attention in large language models, it could mean multiple things. Here, we're going to talk about the general idea of attention. So basically, there are different ways how you can implement this. That's what I'm saying. We're just talking about the general idea of attention. So, for example, for us as humans, it's quite easy to determine that in the first sentence, the animal did not cross the street because it was too tired. It here refers to the animal because we're kind of making the association with tired and animal, and we know that, that's connected, but it's not as easy for a computer to do that. The same thing here. The animal didn't cross the street because it was too wide. Here we know that the context changes, and it in this sentence refers to the street. It's not the animal anymore. So for us, it's easy to kind of determine that. However, for the models, for the computer, is not as easy. So basically, through this layer of attention, the model learns to make this over thousands and thousands and thousands of examples. It kind of learns to make to make these associations between words and how all of the words in a sentence are related. Because basically, how these models generate text is that they generate one token at a time, and for each next token, they need to generate everything that was said before. So at every specific point, the model needs to have a representation of how everything else is related to each other, so that it helps them to kind of be able to predict whatever should come next. Okay, having said that, how do we actually do the training? How do we actually train a model? Basically, there are 3 stages. This could, I mean, it could vary depending on who you ask, but these are kind of the general three stages that you want to apply. First of all, it's the biggest one and the most expensive stage, and this is the pre-training stage. This is a stage where we just send massive amounts of text to the model, and this is not structured in any way, shape, or form. So basically, this is just data as raw text. It could be articles, blog posts, forum entries, or whatever. So basically, how the big guys do this, they scrape the whole internet and they just use whatever they found. They're not even trying to do any extreme cleaning or deduplication. There might be some that is like basic stuff, but you're given the amounts of text that go into this phase, it's impossible to do anything that it's very precise. So basically, you're trying to remove some fluff, some duplicates, some maybe inappropriate stuff if you're able to do that. But otherwise, you just stuff all of this text into the model, and then this phase we need a lot of resources, and it takes a lot of time. So basically, after this phase is done, what we get in the end is a model that has this knowledge in it, but it's not very able to kind of apply that knowledge. So it has this knowledge, but it's not very useful for end users. Basically, it's a very expensive autocomplete, if you can say that. So basically, for example, we have examples here for each of the after each of the training phases, how the response might look like. So the question is the same everywhere, and the question is, what is 2 + 2 - 1? And this is maybe not the most appropriate question for these models, because they're not particularly good in math. But however, it's a good example. So for example, the question is, what is 2 + 2 - 1? And now after this first phase, the response might be 3 dot, what is 3 + 3 divided by 2? So basically, the model kind of learns that it needs to respond, but then from all the data that it has seen, it kind of thinks, okay, we need to continue generating. So it's not able to just answer and stop. It continues generating. So the next, it might generate like another question, then another answer, another question, another answer. So basically, it has the knowledge in it, but it's not able to apply it in a way that it's going to be useful for end users. Now, the second phase is called fine tuning, and in this phase is where we actually teach the model how to use the knowledge that it has. So basically, in this phase, we're teaching it how it should answer questions, how the answer should look like, etc. So basically, we take the model that we got from the previous phase, and in this phase, we feed it with question answer pairs. That's the easiest way to explain them, and then we have some examples later on to actually see how they look like. So basically, just a question and the expected answer, question and the expected answer. Through these instructions, this is called instruction tuning. Through these instructions, we're actually teaching the model how to use its knowledge and how to formulate answers that are actually useful to end users. And so here, the same question, the response might be just 3, and that's it, because that's actually the answer to your question. And now not the final, but let's say the third phase is learning from human feedback and preferences. This could be done in different ways, but the general idea is that this is a further alignment of the model of how we like it to behave. For example, in this phase, you're supplying multiple possible answers to the model, and you're awarding or penalizing the model depending on which answer it chooses, and that's how you're teaching it how the answer should look like. For example, in this phase is where OpenAI, for example, handles how ChatGPT answers for sensitive topics, like, I don't know, how do I create a bomb or something like that. Basically, it's not allowed to answer those questions, and this is where they teach it not to do that. So, for example, the same question here, the response might be, to solve the problem, we need to perform the operation, blah blah blah. So basically, it's giving a bit more context, a bit more explanation, if that's our goal. So basically, here we're actually trying to expand on the previous phase and kind of try to really align the model and get in the way that it answers questions and how it does that. Okay, now regarding MKLLM 7B, as I said, we're going to go through this example and we're going to see all of these phases. We're going to actually see the resources that were used, the instruction data and or the pre-training data, etc. So basically, regarding MKLLM 7B, it's based on Mistral 7B. So the idea is that we did not start from scratch here, simply because starting from scratch is going to take a lot of money and time and resources. So basically, if you're a smaller lab or an individual or a group of people, starting from scratch is really, really expensive. So the idea was, that we're going to take Mistral 7B at that time, which when you prompt the base model, it was really not able to speak the Macedonian language. And the idea was that we're going to take it because the model is already trained on some other languages. So we're going to try, the idea was to, let's see if we can try to teach it a new language. So the idea was we take that model, we train it additionally on a Macedonian corpus, and then we develop two instruction fine-tuned variants. One of them is instruct, and the other one is translate. And we're going to talk about why we created the translate version next. So regarding the base model, as I said, we took Mistral 7B, and then we train it additionally with a data set of 300 million tokens, primarily from the Macedonian Wikipedia. And we did this in two epochs, meaning we pass the same data twice through the model in order for it to learn. Just so you have some sense of the size of the data is, as I said, the idea was that we did not have a lot of money to do this. So the idea was to, let's see if we can do something that is going to be useful, but without spending thousands of dollars. And 300 million tokens, just to put it in to get an idea of the scale, it's not that much. Actually, it's quite little. For example, the latest Llama model was trained on 15 trillion tokens. So we're talking like a lot more. And for example, the idea is that even if we do not have such a massive data set, we actually got something that was quite performant. For example, the latest Llama was trained, I think, for 20 days on a cluster with 16,000 GPUs. So we're just talking about like really massive numbers of compute. Regarding the compute that we had, we used for the continued pre-training, we had 8 NVIDIA RTX 6000 GPUs. Each of them has 48 gigabytes of memory, so a total of almost 400 gigabytes of total memory. And it took us 30 hours on this cluster on this node to finalize the training. Actually, the two epochs. Now, after the base model was done, the next phase was to start the instruction tuning. However, the problem was that we did not find there weren't any instruction tuning data sets for the Macedonian language. So basically, we need to figure out a way, how do we translate some existing, because for English mostly, there are open source instruction tuning data sets. So the idea was to how do we translate them? And the first idea we had is, all right, we're gonna try to train a translate model ourselves, and then we're gonna use that translate model to kind of translate additional instruction tuning data sets. And that's what we did. We didn't end up using this in the end because we got to some OpenAI credits, and then we used those for translating. But however, we have the translate model, which works quite fine. To do that, we had a data set of 125 million tokens, around 150,000 samples. And these are actually, we had 75,000 unique samples because we had the samples in both directions. We had an instruction translate this from English to Macedonian, and instruction saying translate this from Macedonian to English. For this phase, we had 8 GPUs again, but smaller ones, A5000, which have 24 gigabytes of memory. Why do we have the smaller ones? Simply because for fine tuning, you're always going to need a bit less resources than doing the whole pre-training, continued pre-training, and especially if you're using some if you like PEF techniques. The idea is that you don't have to train the whole model for fine tuning. You might train just specific layers of the model, and you can do that in lowered precision, which means that you could get away with fine tuning a model with a lot less resources, which kind of ties back to what I said at the beginning, that for fine tuning, if you have an area that you want to specialize a model for, you don't have to, you don't want to learn, teach it a different language, but just an area that you want to specialize in, then you can get away with a lot less resources and a lot less GPUs and get something that is really, really performant. Now we're not going to go into the technical details here for the QLoRa config, but this is for example an example of how the data set looked like for this model. So for example, we have an instruction: translate the following text from English to Macedonian, and then we have the input, the English text, and then the output is the Macedonian text. And we had 75,000 of these examples. We passed them through the model, and then the result that we got is actually was quite performant. So basically, on this chart here, we can see that only Google Translate at the time had a better performance, and we compared the model with other models similar to its size or that are used for that function. We even compared it to, at that time it was Llama 3, the latest version from Meta, and the biggest one they had was 7 dB, and our model performed better than for translation, better than that's Llama. And now for the instruct version, so basically this was the translate version, and now we have instruct version that actually could be used to kind of communicate with users, with end users. For the data here, we had 85 million tokens, which was 80,000 samples, and it primarily came from two data sets, one of them called Capybara, and the other one called Dolly 15K from Databricks. According to me, even now, these remain to be one of the best instruction tuning data sets, because especially Capybara, because it has a lot of multi-turn conversations. Basically, not just question answer, but you have question answer, another question, another answer, as we see here, which is very, very valuable for training, because if you only have single question answer pairs, single turn question answer pairs, it might be a problem for the model to kind of learn to hold that conversation if you have multiple turns. Here for the compute, we also had the same cluster with the A5000 GPUs, and additionally, we did a full fine tuning with with bigger GPUs just to see what kind of performance we get, and these are the times. Regarding this is actually how a sample from the data set looks like. So for example, we have some system prompt, which could be whatever. This is a prompt that could be used to kind of prepare the model for what kind of conversation we're about to see. And then we have one interaction from the human, like which book series features the characters of Harry, Ron, and Hermione attending a school of witchcraft and wizardry. And then the model answers Harry Potter. Then the human has another question, the model answers, which kind of, all of these questions kind of follow the initial context. That's why I'm saying multi-turn conversation data sets are very, very important. So basically, the outcome of this model was quite good. We translated some evaluation data sets, and we put it against all the other models that are in the same size at that time. So basically, we compared it with Llama 3.8b and Mistral 7b Instruct, and we performed better than both of them. And another note here is that these evaluation data sets primarily evaluate the model on choosing the right answer out of a group of out of a multiple choices answer. So basically, they have a question and then multiple choices, and which choice does the model choose. So the idea is that it tests primarily the reasoning of the model, not its ability to generate coherent text. And I think that on that scale, for that evaluation, the model performs even better than these other models. If we tested, if we wanted to generate actual text, that's where this model shines a lot more than its competitors in the same size. Finally, regarding the resources, now these are for the Macedonian language, but if you're interested in UK, these are actually translated data sets, so you can find the same data sets in English as well. We have evaluation data sets, as I mentioned. These are the data sets that we use for evaluation: ArcEasy, ArcChallenge, and Vino Grande. All of them are multiple choice questions, and we have them in Macedonian, of course, as part of the project, but also you can find English versions online together. Now there are some other evaluation data sets as well, but this is just by the way, all of this is available in Hugging Face for the ones that are not maybe familiar with it. But Hugging Face is sort of like let's say GitHub for ML and AI stuff. Basically, you can find all of the models, data sets, etc. over there. So basically, you have the licenses for each data set or model, and you can find whatever you need there. Not only text data, but also images, audio, and everything else that that you might need. Now, as I said, I do have a short demo because the idea was that we trained this 7B model, which is 7 billion parameters. The good thing is that these models are small enough that you can actually run them quantized. You can run them on a consumer grade laptop, for example. I have a Mac with 16 gigabytes of RAM, and we can actually run this model here. Let me just first of all, for the translate, I have an example here prepared. So the idea is that we need to translate this text from Macedonian to English, and as you can see, for consumer grade, this is quite fast. We're getting pretty good tokens per second output here. And now for the ones that do understand Macedonian, you're going to see that the actual output is the actual translation is quite good. It's actually exactly what the original text in Macedonian says is what we get in the English version here. And I have one more example that shows right now everybody's talking about agents and tool calling and stuff like that. And even though this model is not trained for that, I think, for example, during its instruction tuning, it was able to pick up some interesting stuff. So, for example, if we test it to see how it performs for function calling, you can see that, for example, here this is even in English because it's just a quick test. The idea is that we have a bunch of functions that the model should call, and then we say, all right, the request is send a text to John saying I'll be 15 minutes late. The model correctly chooses the function, the parameters. So the parameters being to and message, and we have this function here, which all right, we have this function, figure out what the user is asking for, and figure out which function we should use and what are the parameters that we want to call. And as we see, it shows the correct function and it shows the correct parameters. Or if we say like order coffee. Again, we have a function here that is for ordering food and drinks, which is order food. The parameters are restaurant item quantity, and it's able to kind of fill in the restaurant, the item, and the quantity that we need. So, as I said, even though the model is not trained for this, we can see that it can handle basic questions. And that's everything that I have prepared for you.